Nike, are you going to start the recording?
Yeah, it's recording. Go ahead.
Okay, excellent. All right. Hi, everyone. Welcome to the high dimensional seminar. Today we have Adam Klivans from UT Austin. We're very fortunate to have him speaking about computational statistical gaps for learning neural networks. So take it away, Adam.
Okay, thanks, Salil. Thanks for having me. Thanks for inviting me. And before I begin, let me just plug this new, at UT, we're the headquarters for this new NSF AI Institute, one of these AI institutes. And our theme, we were given an award in the Foundations of Machine Learning track. So we're now the home for this Institute for Foundations of Machine Learning. It's called IFML. And we're aggressively recruiting postdocs. We're going to be having a lot of, foundational ML programs. Some stuff will be joint with Simons, upcoming Simons programs. We'll be recruiting jointly fellows with Simons. But if you're interested in a postdoc, please apply. You can just email me or Alex Demakis. There are instructions, and if you see there's a link there. Postdoctoral positions are available, and we have a team of people. So I'm the director, and Alex Demakis is the co-director, and then we have a really amazing team of researchers from UT Austin and UW, and also Microsoft Research, Wichita State University. So if you're you can have the chance to work with all of these people. So I encourage anybody who's interested to apply. Okay, thanks for letting me do some shameless promotion. Anyway, yeah, the talk title is Computational Statistical Gaps for Learning Neural Networks. Can you hear me? Am I still broadcasting okay?
Yeah, we can hear you.
Okay, great. So what I'm really interested in, where I'm really coming from, is an algorithmic question. So this line of research is really interested in the question of what are the most powerful algorithms for learning neural networks? And it's a question that's super important, but I think we may have lost track of a little bit. I think right now we sort of take for granted that the current best algorithm that we have for training or learning neural networks is backpropagation, or algorithms that are based on gradient descent. And the question that I've been thinking about for the last several years is, is that all there is? I mean, gradient descent, backpropagation, it's an incredible algorithm. It's a great algorithm. It's had a lot of success, but sometimes we don't even stop to think that, there might be potentially a better algorithm for training neural networks, or there might even be some, say, pre-processing steps that we want to perform that you could use in conjunction with backpropagation or gradient descent. And I think that these are super important algorithmic questions, given the importance of deep learning and training neural networks, and they're a little bit overlooked right now, in my opinion. So the analogy that I like to make for this line of research is basically an analogy to sort of the simplex method. Also, an amazing algorithm used to solve linear programs all the time. But it took a long time before I think most people would agree that this smooth analysis paper of Dan Spillman and Shenghua Teng really gave some powerful, compelling, provable guarantees or reasons as to why the simplex method works well in practice. It took decades for this research to appear. And, a complementary set of algorithms to the simplex method would be interior point methods. That was, a major breakthrough in optimization and algorithms, gave the first, polynomial time efficient algorithms for solving linear programs. And I would argue that right now, sort of stochastic gradient descent is like our modern day sort of simplex method. It works really well in practice. It's very simple. It's a great algorithm, but it turns out to be very difficult to analyze, and we don't quite understand why it works. And even worse, we don't have really a complementary set of algorithms for gradient descent the way we do for the simplex method. And so what I'm really interested in is coming up with, not maybe the word alternative is a strong word, but at least a set of algorithms that are perhaps complementary to gradient descent, where we can reason about their runtime, and we can give provable rigorous bounds on things like convergence, sample complexity. Okay, so before I dive in and explain the algorithmic problems that I'm looking at, let me just mention two models of learning. Many of you, I'm sure, have seen them before. These are just, if you've heard of the student-teacher model or pack learning, so on and so forth, these are all basically the same. The model is that I receive these examples, xi and yi being the labels, drawn from some distribution d. And I'm going to assume that y is actually equal to c of x for some concept c in script c. And so you can think of script c as a class of neural networks. It's just a function class. And the goal here is going to be, after seeing, you get to draw a bunch of these examples, and then you want to output some classifier h whose test loss. So I'm not really interested in training loss per se. I'm interested in test loss. So you want to output a hypothesis h whose test loss is small, less than or equal to epsilon. And I'm using square loss here just for simplicity. And I may refer to this as sort of a regression problem because we're looking at square loss. So this is one model of learning that I'll be examining. So I'm calling that regression. And then there's also the classification problem. And in the classification problem, your labels y here are always going to be Boolean 0, 1. And with the guarantee that the conditional mean function is equal to c of x for some function c in script c. So, y is a Boolean label, but the expectation of y given x is actually equal to c of x for some, say, neural network in some class of neural networks, script c. And then again, we want to output a hypothesis h classifier whose 0, 1 loss, instead of square loss, we want 0, 1 loss to be small. So we want the probability when you draw a new example that h of x does not equal y is less than or equal to epsilon. And this is the p concept or probabilistic concept model due to Kearns and Shapiro. Okay, so one model is just regression. The other model is classification. And just some other preliminaries. So I'm going to be looking at this problem from, arguably sort of the most well-studied, natural setup. And that is, we'll start with script C being a one-layer neural network. And by that, I mean, concretely, it's equal to the sum of k hidden units. So you have these lambda i's, these are the weights. And then you have these w i's, these are the hidden weights, the hidden units. And you have this sigma here, it's an activation. You can think of sigma as being ReLU or tanch or whatever nonlinear activation you'd like, but I'm going to be thinking about ReLU probably for most of the talk. And so y is just going to be equal to your output here is just going to be, in the regression case, it's just going to be equal to this linear combination of nonlinear activations. And the other sort of assumption that I'm going to assume is that the marginal distribution on X is Gaussian. And so, sometimes I would say at this point, this setup is sort of canonical. If you look at the literature on, learning neural networks over the last, say, 5 years, there are probably, dozens of papers written on this particular problem in this particular setup every year. Okay, so it's a very natural test. Yeah.
Adam, can I bug you with a question?
Sure.
Can you comment a little bit on why I know you say this is canonical, but maybe just commenting on the field then, why small test error is a reasonable goal here? I thought that there's some notion that the generalization performance of SGD in practice is not necessarily well explained, or maybe it's controversial whether it's well explained by it achieving small test error. Something about it finding some kind of special sets of parameters that have small test error and also happen to generalize well. So given that you're looking for alternatives to SGD, why is this the right metric?
I didn't totally understand your question. I mean, it's the gold standard for metrics. You want small test error as opposed to small training error. I mean, it's trivial.
Oh, sorry, you said, I'm sorry. I'm just, yeah, good point, sorry. I just got confused about test sets and training sets.
Yeah,
because I would have said generalization.
You want small generalization error. People mean different things when they say that, so I try to avoid that word. But I'm just pointing out that, and I'll talk about that in just a second. But you know, you want your model to actually have predictive power, and so the way you would measure predictive power is that it would have small test error, not necessarily just small training error. Yeah.
Great. But, sorry.
No,
I literally thought you
I'm glad you
said or
pointed that
meant
out
training error.
There's
Great.
And yet there's still a lot of confusion about that, and I'll talk about that in just a minute. Okay, so as I mentioned in the abstract, this problem is information theoretically easy. You know, pick your favorite measure of complexity from neural networks. It could be something very classical like VC dimension. You could use something slightly more modern, such as Rademacher complexity. You could merely count parameters. Pick your favorite measure of complexity. We know that the sample complexity for learning one-layer neural networks is polynomial in every parameter that appears. So D, the dimension, K, the number of hidden units, 1 over epsilon. You know, if you want to add a parameter in there for probability of success, you can do that as well. We know that. What we want is an efficient runtime. And I guess I want to emphasize that at a minimum, we want our running time to be polynomial or at least sub-exponential in the ambient dimension D. And the reason for that is that, as you recall, I'm really interested in algorithms. And if you allow me to run in time exponential in the dimension, then typically I can do some sort of just brute force search over all possible, you know, using a net of potentially all possible neural networks of a particular size. And, you know, the learning problem from an algorithmic standpoint sort of becomes trivial. So, of course, you would like to be polynomial in all the parameters, but you know, really, the most important one to be sub-exponential or polynomial in is the ambient dimension D. Okay, so let me just remind you that you know, what happens if P equals NP? Well, then it turns out that, you know, all of these learning problems, maybe it's sort of easy to see that all of these learning problems turn out to be easy. And why is that? Well, I can take a large number of examples drawn from this distribution, still polynomial in all the parameters. By large, I mean, say, a large polynomial. And then what I can do is use my non-deterministic power to guess a one-layer ReLU network of smaller size than the training set that I've chosen that has low square loss. There must exist one because we assume that all the labels are coming from, are labeled exactly according to some one-layer neural network. And so I can just guess one. And then I can apply any of these classical theorems of generalization because I have a one-layer neural network that's smaller than the, of size that's smaller than my training set. And so you can apply any of these sort of classical bounds and you can prove just immediately that it will also have small test error. Okay, so if P equals NP, you really are in good shape. And I'm just highlighting that this is inherently a computational problem. Unfortunately, as it turns out that, you know, if you look at the literature on you know, training computationally in computational learning theory on training neural networks from, say, you know, the late 80s and onward, most of the results that we have regarding, you know, finding these classifiers with low error, low test error, are negative. So there's a classic result of Blum and Revest, I think from 88 or 89, that shows, and a lot of people cited, it shows that finding small networks with low training error is NP hard. And the setup that they have in their result really crucially uses the fact that you're working with discrete distributions and discrete labels. So the nonlinear activations are threshold, so they're not continuous, so they're not ReLU or Tanch or something. And the training sets themselves are they're discrete. They have Boolean features. And I guess, if you look at the literature on these types of hardness results, it just becomes very clear that learning problems over discrete domains can really encode what are thought to be very computationally hard problems, such as NP hard problems, but also a variety of cryptographic problems. And the takeaway message is really, if you want to learn Boolean functions over discrete domains, you're in trouble. I mean, life is very hard. And I think that some people sort of started to get a little disillusioned with some of these results because, I think what people really wanted were positive results. They wanted new algorithms for learning, rich function classes. And instead, the field sort of, proved a very rich and, in my opinion, very interesting set of hardness results. So some people were a little disappointed in the results that came out of this kind of line of research. I personally think that they're terrific, and I'll explain why I feel that way later. I think these hardness results are super valuable and continue to be super valuable. But I think that some people were a little disappointed by them, especially when sort of you look at the resurgence of deep learning and deep learning theory. Given the performance in practice, I think some people began to look back at these results and sort of said, well, they're nice, but they're not really meaningful with respect to what's going on, quote unquote, in practice. So that brings me to a result that I want to tell you about with my students, Surbi Goel, Arvind Golakata, Jihan Jin, Sushrid Karmakar. This was an ICML just recently in 2020, and the title is just Super Polynomial Lower Bounds for Learning One-Layer Neural Networks Using Gradient Descent. And what we show here is that really learning even one-layer neural networks, even when the marginal distribution is Gaussian, is still a very hard problem. It's not necessarily just because you're working over a Boolean domain or that you're encoding sort of discrete NP-hard combinatorial optimization problems or even cryptography. So what we show is unconditionally, if you would like to learn a one-layer neural network, even if the marginal distribution is Gaussian and you're going to run gradient descent, then we can prove unconditionally that you cannot achieve a polynomial in the dimension runtime to obtain small test error. It's just not possible. And in particular, this rules out several common approaches that people have been looking at for learning neural networks, such as using NTK or the neural tangent kernel, or looking at a mean field approach, this sort of particle-based approach for coming up with neural networks. It rules out overparameterization. So a common technique, or a common technique that's studied right now, is you overparameterize, you're trying to learn a small network, you form a very large network, you run gradient descent on it, and you hope for the best. And our results show that, in the worst case, or although, even when the distribution is Gaussian, even in the simplest case, these approaches are just going to fail.
Adam, a quick question. Does the initialization matter here?
No, it doesn't.
Something?
Nope.
One more question, Adam. So I mean, so are you also ruling out, what is it exactly that you're ruling out? Is it the case that if you have, exponentially many gates in your first layer, gradient descent could still possibly do it? Or maybe you'll get up to this in the future slides. Yeah.
I'll be more concrete in just a second.
Cool. But
I mean, yes, if you're willing to, so it actually rules out, just looking ahead, it's going to rule out any, correlational SQ algorithm that uses a polynomial number of queries. So if you want to, so even if you use an exponential size network, but you're only training it for a polynomial number of steps, you're still not going to succeed.
Excellent. Thanks.
Okay, so just to elaborate a little bit on this, ruling out these other overparameterized approaches, sometimes I get asked the question, well, I thought that, if you use NTK, it solves this problem. And going back to Sam's question, no, it doesn't. Basically, the upshot of, a lot of research on the neural tangent kernel is that if you run gradient descent on an overparameterized network, then this overparameterized network will quickly achieve small training error, which is interesting. But if you want to prove that this network actually has low test error, then you need to prove some sort of generalization bound. And in order to do that, you need to take more assumptions. And typically, the assumptions that are taken are that your overparameterized network has small model complexity with respect to some measure of model complexity. And once you do that, then you can sort of immediately apply one of these classical generalization bounds, because we know that if the classifier that you happen to get is of low complexity, then it will generalize. And so if you look carefully at some of these assumptions, they basically just sort of immediately imply that your model has low complexity. So yes, of course, then it will generalize. But these require an assumption. And these assumptions are essentially of the form, well, yes, it generalizes. Okay, so we're going to prove two types of statistical query lower bounds for this problem. And I need to make this distinction for reasons you'll see in a second, but there's this CSQ model and the SQ model. The SQ model is more general, the CSQ model is more restrictive. In the CSQ model, C stands for correlational statistical query. The learner, in this particular model, the learner, so instead of getting to see examples drawn from the distribution, instead what happens is the learner picks a query function phi and receives the expectation of phi of x times y, the label, to within some tolerance parameter tau. And then in the more general SQ model, the learner picks phi of x comma y and receives the expectation with respect to the distribution of phi of x comma y to within some tolerance parameter tau. And the nice thing about the CSQ model is that gradient descent you can show pretty easily that gradient descent is a CSQ algorithm. Okay, if you want to get an estimate of your gradient, you just differentiate, and you'll see that you can just plug in the gradient for the appropriate function for phi of x there, and if you look at expectation of phi of x y, you'll get an estimate of the gradient to within some value tau. Okay, so let me show you the actual construction itself for the lower bound. And it turns out that if you want to prove a CSQ lower bound, then it suffices to find a family of one layer. Here we're talking about ReLU. So let me focus on ReLU for just a second. But it suffices to find a family of one layer ReLU networks that are almost pairwise orthogonal. That is to say, you want to come up with a family of functions, capital F, such that if you look at any F1 and F2 in capital F, the expectation with respect to x drawn from your distribution of F1 times F2 is very small. Okay, and I just want to point out, so that's really what you need to find to prove one of these CSQ lower bounds. And for discrete distributions, so if you allow me to use discrete distributions like the uniform distribution over the hypercube, then it's pretty easy to come up with this family of functions just using the parity function. So we know that parity on different subsets of input bits, parity functions are pairwise or are exactly orthogonal. And it's also not too hard to see that with respect to a discrete distribution, a one-layer ReLU network can compute parity. Okay, and so you'll immediately get these super polynomial lower bounds by taking parity on different subsets of input bits and then finding the corresponding one-layer ReLU network that exactly computes this parity function. So it's very straightforward if you're allowed to use a discrete domain. And what is more difficult for our situation is that the marginal distribution is Gaussian, and so there's no sort of parity function that we can try and compute. Okay, so here's the construction. Remember, D is our dimension, and so you're going to fix some subset S of D of size K. And then I just have two functions I need to define. So G sub S is the sum over all W strings of length K. And this chi here of W is the parity of W times phi, which is, think of this as ReLU, of W inner product X, the bits according, the bits of X indexed by S, then you have to divide by root K. So, right, you might be thinking, oh, wait, G of S of X, you're using the parity function. Well, this is just a coefficient. This chi of W is just +1 or -1, depending on what the parity of W is. GS of X is not computing parity. Phi here is, say, ReLU, and so you're looking at W inner product X indexed by S, and then you're taking the sum over all of these, you're kind of summing up over all these different +-1 coefficients. And then finally, I'm going to define this function F, which is some function, odd function psi of G of S of X. Okay, so you're just going to run GS of X through psi for any odd psi. And in particular, psi could be the identity function. So, I could just use GS of X if I wanted. Just two things to note. So the size of our family is roughly D to the K as you enumerate over all subsets of D of size K. And then each network, so G sub S, has 2 to the K terms. That's because I'm summing over all W and -1 to the K, so it has 2 to the K terms. And here you can see that I can choose K to be roughly log D, and I will get a family that has super polynomial size, and so will require super polynomial number of statistical queries. But each network actually only has 2 to the K terms, and so each network will be of polynomial size in the dimension. Okay, so that's the construction. Any questions on the construction? This is the family. And this works for any activation, not just ReLU, it works for any nonlinear activation. Okay, so, oh, right, so I'm going to prove this. So just to show you how simple this is, I'm going to prove to you that these families are orthogonal. And we'll use this little fact that I have in this orange box, which says that if you look at f of s of x, and then you entry-wise multiply it by z, you get the parity of z times fs of x. So you can just pull out the parity of z. This is a simple fact.
Z is a sign. I mean, Z is signs, right? I guess.
Yeah, Z is yeah, right. Thank you. Z is +-1. It has +-1 entries, right? Okay, so I want to show you that. For any two different subsets, or S and T, the functions are in fact orthogonal. So I want to prove that expectation of x, f of x times ft of x is equal to 0. And equivalently, I can just look at first picking some z that has +-1 entries, and then looking at x. I can do this because of the sign symmetry of the Gaussian. So this is the only place where I'm using the fact that the distribution is Gaussian. In fact, this property holds for any sign symmetric distribution. And then I can use the fact and pull out my z's. Sorry. And then here I have these two parity functions. And as we mentioned, any two distinct parity functions, we said s does not equal t, is going to be 0. And so that's just going to cancel everything out. And you're left with 0. So they're perfectly orthogonal. Okay, good, simple. Okay, so it turns out that the tricky part of the proof is to show that the family of functions is non-zero, so that you're not just redefining, like all these functions aren't just exactly the zero function. And it's a little tricky, but it can be done by looking at the appropriate Hermite expansion. And what we do in the paper for other reasons is we actually quantitatively show how far away these functions are from the zero function. And admittedly, to do that, we need to use one theorem from complex analysis. But once you have that, you're done. So this will give you the CSQ lower bounds, and it will give you a quasi-polynomial lower bound, quasi-polynomial size function family that translates directly into a quasi-polynomial CSQ lower bound. Okay, so as it turns out, CSQ algorithms are not the same as SQ algorithms. For real valued functions, it's easy to see, for example, that if you want to learn Hermite polynomials, take the family of all Hermite polynomials. They're all pairwise exactly orthogonal. So you can't learn them using a CSQ algorithm, but there is a result due to Andoni et al. That does learn the Hermite polynomials in time roughly 2 to the d instead of, sorry, I should say like 2 to the k, where k is the degree of the polynomials, as opposed to d to the k, which is what you would expect which is what you would conclude for any CSQ algorithm. But we can still obtain the general SQ lower bounds for classification. If you want the full SQ lower bounds, we can do that. And the way we do that is we look at the associated classification problem. So, previously we were obtaining these CSQ lower bounds, for this regression problem. If you move to the harder case where you want to do classification, you can show that you'll get the full SQ lower bounds. So if you take a one-layer neural network and then run it through a softmax, you can show that there's no general SQ algorithm for obtaining small test error in polynomial time. Oh, yeah, good. And so let me just mention some prior work along these lines. There was a paper by Song, Vempala, Wilms, and G that gave some type of SQ lower bound for learning one-layer neural networks, but it held only for small tolerance queries. So in particular, it only held for gradient descent on small batch sizes, and it also required very sharp activations. And then there is some independent work by Diakonikoulos, Kane, Kantonis, and Zarifas that gave us an exponential CSQ lower bound. We got a quasi-polynomial CSQ lower bound. For the case of Gaussians, they actually get an exponential CSQ lower bound using a more sophisticated construction. So our two constructions are actually the same in 2 dimensions, and then they use a more sophisticated lifting from 2 dimensions in order to get an exponential lower bound.
Is the exponential lower bound for any activation or for a particular activation?
It's for any non-polynomial activation. So in particular, so if you have if you want to learn a network of size k, then it's for any activation that has a non-zero Hermite coefficient above level k.
Okay.
So in particular, if it's a nonlinear activation, then you have infinitely many, and so everything is fine. Well, if it's non-polynomial, I should say. And we also actually did some experiments just to sanity check what was going on. And so these experiments are really simple. Let me explain them. So the red line here is training loss. So what we did was we took this function family and we generated a training set. And then we generated an overparameterized neural network and ran gradient descent on it. And you can see, as you would expect from the literature, the training loss in red here pretty quickly goes to 0, whether you're doing classification or regression. But the test loss, which is the blue dashed line, it just stays very high the whole time. I mean, it's just gradient descent, even on an overparameterized network, is just failing to achieve small test loss. And this green line here is on the left-hand diagram, that's the Bayes optimal classifier. So you really should be able to, you would hope that you could achieve like 0-1 loss close to the green line, but instead, when you run gradient descent on an overparameterized network, your test loss is just very close to 1/2. Okay. So just to summarize, let me see how much time. Okay. There's no CSQ algorithm that can learn one-layer neural networks in polynomial time. On the other hand, as I mentioned, there are all these papers out there that are written on learning one-layer neural networks. So what's in these papers? Well, and they're very interesting papers. There's a lot of really good work. I don't mean to diminish that, but these results typically require assumptions in order to obtain small test loss. Let me mention roughly how they work and what sort of assumptions they need. So there's this recent paper that I mentioned by Diakonikolas, Kane, Kontonis, and Zarifas. Well, all of these works are sort of tensor methods. So that's primarily been sort of the only tool we have for learning one-layer neural networks with respect to Gaussians. And what they do in this DKKZ paper is they look at this matrix. It's the expectation of y times xx transpose minus identity, and then they run PCA. And what they prove is that the relevant directions of your hidden units just sort of pop out once you do that, and then you can run brute force search in the relevant subspace. But this only works if the coefficients, those lambdas in your one-layer neural network, are positive. And it also, all of these results only hold for one-layer neural networks. What's nice about this DKKZ result is that it doesn't require anything else about any other assumptions on the hidden weight vectors, but it does require the lambdas to be positive. And then there have been many papers that have explored sort of tensor decomposition algorithms in the context of learning one-layer neural networks. This started with a paper due to Jansman, Seji, and Anand Kumar. And for certain activations like tanh, you can look at this third-order tensor expectation of y x tensor 3, and you can do some tensor decomposition. And again, you will find you will actually find the hidden weight vectors. You'll do parameter recovery. What assumptions do they need in order to get this to work? Well, they require positive, like DKKZ, they require positive coefficients on the lambda i's. And they also require that these W's, the hidden weight vectors, are well conditioned, or just maybe an easier way to think about it is the WI's, the hidden weight vectors, have to be almost orthogonal for their techniques to work. And also, as you can see, all of these techniques are CSQ. They're just looking at expectation of y times something. And so there's really no hope that these types of algorithms or analyses can be adapted to learn general one-layer neural networks. And I should also say that these techniques also only seem to hold for one layer. They critically use the fact that the underlying neural network can be written as a one-layer neural network.
Adam, can I ask another question? Like, what if the activation is odd? Can't you just assume the coefficient is positive in the last layer? What exactly happens in this case? So the lower bound still applies, but
I guess I'm okay. I guess I see. So for ReLU, you cannot do that.
Yeah. But like if it was tanh, then you could assume it's positive.
Yeah, but then I see. And so, right, I guess you're saying that's true. For tanh, you could do that. You still need this sort of conditioning assumption, I guess, for the weight vectors. Sorry, what was was that your question or?
Yeah, that was the question. Yeah.
Oh, okay. Yeah, for odd activations, for one layer, it's okay to assume they're positive. Yeah. Okay, so I guess the point is that without taking further assumptions, all these approaches still require exponential time in the dimension, even for learning one layer, if you're looking at, say, a ReLU activation. And a really natural question is, are these assumptions necessary? Can we do something smarter than brute force search just to learn one layer in neural networks? And so let me briefly talk. How much time do I have left, Salil? Or 10 minutes or?
You can, so you have 10 minutes officially, but if we go over 5 minutes, it's not a disaster. Yeah,
it should be okay. So so what I wanted to talk about is our main positive result, and this is joint work with Satan Chen and Raghu Meka. This is a paper that we just put on the archive, Learning Deep ReLU Networks as Fixed Parameter Tractable. And I want to show you that you can do something that's not CSQ, and you actually can do something that doesn't require any of these assumptions. And you can actually sort of break this one hidden layer barrier and do something for general deep ReLU networks. So, how do I define a higher depth ReLU network? Well, I start with this inner activation, and then you multiply by these weight matrices, and then you compose. So, this is sort of the functional form of what a deep ReLU network will look like. And our main result is that given examples X, Y, labeled according to one of these deep ReLU networks, you can find a classifier G that has small test error. And the running time is a fixed polynomial in the ambient dimension D times some exponential function of only the network's parameters. Okay, so that's our main result, and we don't need any assumptions on like positivity of coefficients, or the condition number of any of these weight matrices.
Which parameter? I mean, maybe you can say like.
Yeah, so there are a bunch. So I have it in 2 slides. Okay. But so before I concretely tell you what the main result is, I just want to point out that it's the first positive result of any sort that I'm aware of for learning ReLU networks or any neural networks of depth more than 2. And even when the parameters are all constants, and I'll tell you what the parameters are in just a second, there's no sub-exponential in the ambient dimension algorithm known. And it also gives the first example of neural networks that can be efficiently learned via some polynomial time algorithm, but provably cannot be learned in polynomial time using gradient descent. Okay, so here are the parameters that you wanted to see. So I'm denoting depth is L. The Lipschitz value of the network when viewed as a function is lambda. The size is S, that's the number of activations. The rank of the hidden units in the first layer is K. So you can just think of the number of hidden units in the first layer being K. And capital B is a bound on the spectral norm of all the weight matrices involved in the network. Okay, and it turns out that you have to depend somehow on this Lipschitz parameter is inherent. I'll talk more about that in just a second. Okay, and so the number of samples that we require to obtain small test error is roughly linear in D, and then a singly exponential function in K, S, lambda, 1 over epsilon, that's your accuracy parameter, and then times B raised to the power LK. And the running time is roughly quadratic, times again this exponential times B to the LKS squared. I don't think it's so important, this S versus S squared. I guess the main point is that it's a small polynomial in D, the ambient dimension, and then some singly exponential function in the remaining parameters. So do these parameters make sense, or?
Yeah, it's good.
Okay. Okay, so our algorithm, it's related to a lot of different problems, but you can think the way we're thinking of a ReLU network is that it's a multi-index model. And by that, I mean, it's just some function. If you think about it, if W1 through WK are the hidden weight vectors in the first layer, then the output of the entire ReLU network, no matter how deep it is, it's just some function of these values. Okay, many compositions are involved, but it is some function of these values. And the key thing that we would like to understand is how to find the subspace spanned by W1 through WK. And because it's a function of just the inner products of these weight vectors in the first layer with X, once you've found the subspace spanned by these WIs, you can try and attempt to do brute force search in that particular subspace. And this problem is related to the Hunter learning problem, which, as you know, is to find or to learn some function that depends on only K relevant variables, in time, some fixed polynomial in the dimension times f of K. It's also related to a problem called non-Gaussian component analysis, sliced inverse regression. And in particular, there's a paper by my co-authors, Chen and Mecca, that was in Colt 2020, that gave a result when f is equal to a polynomial, like f is z squared or something, or z cubed. They gave a non-trivial algorithm for a multi-index model when f was a polynomial. Now here, f is much different than a polynomial. It's a ReLU network, and so the techniques from Chen Mecca 20 don't apply. In fact, the techniques that we have in our paper are totally different. Well, are significantly different, I should say. But definitely their paper, inspired this work. Okay, so let me try and explain the algorithm briefly, and then in one of the upcoming workshops we have in December, the one that I'm organizing, Satan is actually going to give a whole talk on this, and you can get more details from him. But remember that y is just I have this pi here, pi sub v, that's the projection onto the relevant subspace. And y, because it only depends on, say, the k hidden units in the first layer, is some function f of pi v of x projected onto that relevant subspace. And then we're going to form this matrix m sub tau. And it's the expectation of xy of the indicator function that the absolute value of y is greater than tau times xx transpose minus the identity. Okay, so you're basically, if your y value is small, this is just going to be 0. And once your y value is larger than tau, well, then you're going to start kind of looking, you're going to start taking averages of, covariance matrices. And it's easy to see that the vectors that are orthogonal to your relevant subspace are going to be in the kernel of m tau. And what we're hoping for, what you'd love to show, is that the top k singular vectors of m tau just span your relevant subspace. So you can form this matrix empirically, do an SVD on this matrix, and you're just hoping that the top k singular vectors span V. And unfortunately, we don't know how to prove that. But what you can prove is that you will find one direction. Okay, and so here again, now I'm taking this matrix m tau. If you look at the orange box, and I'm looking at the inner product, the matrix inner product with pi v, and it's easy to see that this is equal to the expectation again of this indicator y is greater than tau times the norm of pi v of x squared minus k. So what you're hoping for is that you can choose tau to be large enough so that when the value of your network is greater than tau, the norm of x projected into the space, the relevant subspace v squared, is at least 2k. So this would become, at least 2k. If that happens, then when you look at this inner product, you'll get something like k, that's because you're 2k minus k, times the probability that y is greater than tau. Okay, and so first we need to kind of show some anti-concentration of our network, which isn't too bad. And then you'll use some Lipschitz property to kind of show that like a k will pop out here. So those are two things that we need to do. Okay, so as I mentioned, you're hoping that like all of the relevant directions will show up when you do the singular value decomposition, but instead what we could only prove is that one shows up. And so the question becomes, well, how do you proceed? So it's not too hard to show that you'll get one relevant direction. And then the question is, well, how do I get more relevant directions? So there are two cases. Well, let's assume we've recovered some subspace W of the relevant directions, and we want to move on. So this is kind of the next step in our algorithm. So we have some subspace W. Maybe W only contains one direction, and we want to make it W bigger. We want to get closer to the relevant subspace. Well, case one, f of x minus f projected onto W is actually small. Well, then we're done. We've basically recovered the whole relevant subspace. Case two, so if this doesn't happen, well, what we're going to do is look at this indicator function of y. We're going to subtract off f of pi w of x. We're just going to take the label y and sort of subtract off what we've already figured out. And then again, we'll multiply it by this xx transpose minus identity. That's going to be our strategy. The big problem is that we don't know f. That's what we're trying to learn. So if I want to form an empirical estimate of this expectation of y minus f of pi w of x, I'm in trouble. I don't know what f is. I know what w is. I can project x onto w, but then what is f of pi w of x? So what did we do? Well, we actually try all functions f. And so we needed to prove that first, as you enumerate over all functions f in the subspace, you'll still find a new direction. And we need to prove soundness, i.e. you won't find any false directions. So you won't find any kind of spurious directions. And, there are many complications. First is that we don't actually have like the true subspace W. We only have sort of an approximation to W. And also, as we're enumerating over all possible functions in the subspace, we are only getting approximations to f. We're not getting the true f. So every time we want to find a new direction in this relevant subspace, we actually have to enumerate over all possible ReLU networks, which turned out to be non-trivial in and of itself. And so the key structural fact, like where are we using the fact that this is a ReLU network? Well, we're using it in several places, but one of the key structural facts is this very interesting characterization from, I guess, what people would call tropical geometry. And that is, if you have f, which is some high dimensional continuous piecewise linear function that has capital M pieces, then there exists some subset little m of this index set M, such that f of x can always be written in this max-min representation. It's the max over all j and little m of the min of little I and I sub j of gi of x. Okay, so it turns out for any continuous piecewise linear function, and we know that ReLU networks are continuous piecewise linear functions, that we can write them in this way. And so in order to kind of brute force search, this gives us something that we can use in order to both, one, brute force search over ReLU networks, because we can kind of look at this representation and brute force using this representation. And two, it gives us a quantitative way to bound how close our approximations actually are. So just as an example, if f of x were a one-layer ReLU network, which is I've written here, so this is one layer, and you look at these sets, capital P is the set of all I such that lambda I is greater than 0, and capital N is the set of all I such that lambda I is less than or equal to 0. Well, then you can just write f of x as the max over all subsets of P, the min of over all T subsets of N of WS minus WT inner product X. And the reason for that is that kind of the max player is trying to take all the lambda I's that your input X makes positive, and your min player is trying to, again, take all of the lambda I's that X also makes non-zero. And so you add up all the WS's for the positive coefficients and you subtract off all the WT's for the negative coefficients. And that's why this representation gives you the exact output for the ReLU network. Okay, I'm going to wrap up here. So just to recap, we found one direction. We used filtered PCA on the differences, and we enumerated over all possible ReLU networks. And I guess one important thing to point out is this filtered PCA approach. See, when we were forming this matrix, notice that we have this indicator function here, and that is not a CSQ type query, because we're not just multiplying this covariance matrix by y, we're actually multiplying by the indicator that y is larger than something. So that's why it's not a CSQ algorithm. That's why it escapes the lower bounds that I mentioned at the beginning of the talk. So what's open? Well, still fully polynomial time for one layer. You know, as we showed, or as we discussed, you don't need these positivity assumptions for ReLU networks. You don't need these well-conditioning assumptions. Can you do it? I don't know how to do it. You know, all of our analyses for these higher depth networks are exponential in the parameters. Can you improve any of, can you become sub-exponential in any of them? That would be very interesting. And also crucial to our upper bound or positive result is that we used ReLU. I don't know how to get this to work for, say, TANCH. It really critically uses ReLU in several ways. So it would be interesting to improve that. Okay, I'll stop here. Thanks.
Okay, thanks, Adam. I guess everyone, you know, wave your hands in the air as applause. Yeah, I guess if there are any questions, feel free to ask. So maybe I can ask a question while other people are thinking of their questions. Okay, but so the algorithm that you gave is an SQ algorithm. It's just not a CSQ
It is an SQ algorithm. It is not a CSQ algorithm, right?
Cool. All right. That was my question.
Well, as a follow-up, I think you said this, but just to sort it out again, how does that square with the lower bounds? The lower bounds only apply to CSQ, but you said that some other lower bounds, like the lower bound construction you did in detail is CSQ, but you also have SQ lower bounds.
Yeah, so that's correct. So it's the CSQ lower bounds. Our algorithm is not CSQ, so it's not subject to the CSQ lower bounds.
Yeah.
The SQ lower bounds were for classification. We're not solving the classification problem. It's a regression problem.
Great, thanks.
So maybe can I ask a question?
Sure.
You have this brute force step in the algorithm, which might make you not want to sort of implement it in practice. Is there some sort of version that you can't prove works, but might work that, you know, I guess,
well, no,
can
no,
you turn this result into?
No, this is a good question. I mean, and I think this is what's really exciting about this line of kind of investigating algorithms for learning neural networks, because any small improvement that you make has really radical implication. I mean, I wouldn't say radical implications, but has huge impact, you know, because you're training neural networks. So, you know, you can view the sort of filtered PCA as a pre-processing step. And one thing you could implement is just, you know, run filtered PCA and then run SGD. And that's something that we're working on implementing right now. So as you know, just even having a pre-processing step that improves things would be a game changer.
Anyone
Okay,
has,
well,
more
thanks
questions?
everybody. Don't forget to apply for the IFML positions if you're interested.
All right, thanks, Adam, for the great talk. See you next week.
Okay, bye.
Bye.